Have you ever wondered how bridges work? Today, we're going to learn how torque lets us know that these bridges aren't going to fall apart.
Professor Pazuzu, what's torque?
So, what's torque, you ask? Here we have the definition of torque. Torque is measure of how much a force acting on an object causes it to rotate. Torque can be calculated by using this simple equation here. You simply need to find the force times the radius of the lever arm. Then you multiply them by each other to get torque in Newton meters. Newton meters? One of those.
Wait, how does this apply to a suspension bridge?
Good question! I have to pee. I have returned from peeing. I wet myself and had to change my pants. So, if we want to see our equation in a real life situation, we have a drawing here of a bridge. Since we have this cable here helping it stay up, we're going to multiply the cosine of this angle by the force and radius. Then we'll have the torque on this point when we're calculating gravity and this cable. Now, if we look at our bridge model here, we can get a visual representation of how this cable right here will change the amount of torque required. So, see, here we have an angle, and we multiply the cosine of this angle by radius and force to get the torque. But if we move this closer in, then this angle changes. It actually becomes larger. So the closer we move it in, the larger this angle gets, and therefore the torque required to hold this up is less. Dara, how does the change in radius affect the final torque?
Well, it seems that when the radius decreases, the torque also decreases, because you're multiplying by less. Isn't that right?
Correct! Yeah, that's right. Now, if we look at our equation right here, we can clearly see that if the radius goes down and the angle goes up, then the torque on the point is gonna go down. Yeah! Children, come express to me the knowledge that I have given you in this model.
As you can see here, we have a 250 gram mass.
So we're gonna measure the torque at a 40 centimeter radius. So we hook our weight on here, and then we hook our spring thing. So now we have our string at a 60-degree angle, and we have 40 centimeters and 24.5 newtons, and we can plug that into the equation over there.
It can be shown in the torque equation here with our mass, our radius, and the angle, and it comes out to 4.9 Newton meters.
Yeah, that's some good physics there, boy!
If we move the cable to a 20 centimeter radius, then the angle increases to 70 degrees.
So as we can see over here in the equation, the newtons is still the same, but our radius is half as much, and our angle is 70 degrees. So when we calculate that all out, we get 1.676 Newton meters, which is less than the first equation.
Great job, my little Blumpkins. So we can see that the torque changes in these equations, and that's good.
And
That
Is
our next
torque.
experiment.
No, is it torque experiment?
No, that's our experiment. And we're all going torque.
Okay, my bad.
Oh, we're going torque? Are we singing torque?
Are we gonna harmonize torque? And if we are, who's going high?
Dara goes high, I go low. You go something. Okay.
I want to go high.